Welcome back, Advanced Chemistry 2 students. Hope you had a nice spring break. I just wanted to review Hess's Law a little bit before we got into standard enthalpies of formation, because it does come into play for one of the problems where to put the two ideas together. Just want to remind you that enthalpy is a state function, so it doesn't matter how you get to that place, how you get to that amount of energy. Could be room temperature water that's been heated up from being frozen, or it could be room temperature water that has been cooled down from being at boiling. That room temperature water has the same amount of energy, no matter how you got, no matter what steps, no matter the pathway that you took to get there. Very important for what we'll be getting into with standard enthalpies of production. Here's one example of diatomic nitrogen gas being added to 2 moles of diatomic oxygen to produce 2 moles of nitrogen dioxide. Gives the enthalpy of formation. Okay, we can write this as one step, but to say we didn't know that, we could actually do this as 2 steps as well. So here's the 1-step example down here on the right. Here's the 2-step reaction. Let's say we only knew the 2-step reaction. We didn't know what the standard enthalpy how much energy it took to produce this NO2. So if we're doing this two steps, we could look here. If we knew these 2 reactions to make these 2 moles of nitrogen dioxide, the amount of energy that it takes to make 2 moles of nitrogen monoxide, is 180 kilojoules. The amount of energy it takes to make 2 moles of nitrogen dioxide gas is negative, or releases 112 kilojoules, represented as that negative number. Remember that negative in physics means change direction, right? So it's giving energy off, whereas the 180 kilojoules in that second reaction is endothermic. That energy needs to be put into the reactants to make that product. So our signs here, if you notice, if we took the whoops, just need to move me. If we took the 2 moles of diatomic nitrogen gas, 1 mole, plus the 1 mole. If you notice on both sides they have nitrogen monoxide, 2 moles, right? So if we're adding these together, cancel these 2 out. We'd have 1 mole of nitrogen gas, a mole each from each reaction there to give us 2 moles of oxygen, diatomic oxygen gas, and then 2 moles. And so if we add these 2 enthalpies together, you get 68 kilojoules as your answer there. So looking at Hess's Law, one way you could, if you can't always use that single step, a lot of times it's easier to use the 2 steps to figure it out, and it'd be the same amount of energy. Let's look at this other one here of diborane, which is a highly reactive boron hydride, B2H6. Used to use it as rocket fuel. There's the chemical reaction. Okay, so we have chemical reaction we're trying to end up with at the top. 2 moles of boron plus 3 moles of diatomic hydrogen to give us the diboron hexane. So we've got these 4 reactions with the known enthalpies to try to figure this out. There are some hints here, which I should have given you before we did that other page. Usually there's several reactions. There's some strategies to try to figure these out. Several reactions that you can manipulate, kind of use these mathematical equations. It's a great thing about chemistry. It's all based off of these moles, these mole relationships. What I always do is I work backwards from that reaction that you're trying to find. And then if you, this helps you so you can decide how to manipulate, how to cancel, how to get what you want out of what you're looking for, right? Out of what you have. Anytime you reverse those reactions, you have to remember that it is changes the sign of the enthalpy. And if you multiply any reactions, you have to multiply the entire thing, including the enthalpies. And sometimes it takes many trials and error. Sometimes you have to use fractions. But you can always kind of figure it out. It's kind of like a puzzle, chemistry math puzzle. So if we're back to this example here, trying to combine equations A, B, C, and D. It's a bit smaller so you can see it all. In this example, what I did was broke it up into different parts. And so added these two equations looking at what I'm trying to get here, which is 1 mole of the B2H6 on the right. So you can see taking those first two equations. Oh, let me point this out. If you notice in this reaction A here, you have a fraction for the mole ratio of the diatomic oxygen. You might be saying, well, why is there a fraction? How is that possible you have a fraction? If you notice, on all of these, for the products, these are all 1. Okay, so anytime you have these enthalpies, it makes it a lot more simple to use these enthalpies with these products as 1. 1 mole on each side of it. And so to get that, oftentimes we'll have to use fractions for the reactants mole ratio on the left side there. But it actually simplifies things when you're trying to do this. We get really complicated. Anyway, so here's this first adding these two reactions together. This would be the reaction A with reaction B. So you have the same enthalpy for A, negative 1,273 kilojoules. But for B, if you notice, they made it negative. So they changed the sign by multiplying by -1. You have to change the sign because the reactants was just, the sides were just flipped. So it's the exact same reaction, just flipped. If you notice now, I don't have 3 moles of, you still have 3 moles of O2 on this side. Because there's 2 of them. So we can delete these, gives us a new, when you add these together, you can cancel. If you notice, you have 2 borons, 3/2 of oxygen here. And so if you notice, we have we can cancel out this. What can we cancel out here? We can cancel out some of these oxygens, right? Here we've got 2 borons. We have B2O3, right, on both sides, right? So here we cancel that out on both sides. And what happened here is we have 2 borons, 3/2. So we can simplify this, kind of, because there's 3 over here, right? we have, oh no, we have 3/2. Okay, so the oxygen has been simplified. So this, because we have 3/2 of an oxygen here, we have 3 oxygens here. Mathematically, that would be, if we multiplied both sides by, no, if we divide both sides, no, multiply both sides by 2. 6. How do we cancel that out? So on the left side of our reaction here, we have 3/2 of an oxygen, and we have 3 oxygens. Of course, this is a mixed fraction. This would be 1.5 oxygens, right? Here we have 3, and so we can cancel this 1.5 oxygens. And if we have 3 here, that means we have 1.5 O2s on this side. So that's where this, leaving it as a mixed fraction sometimes makes it easier. So now we have this as our reaction, and now we add the third, the reaction C here, which is H2 half O2 and 1 water. And so you can see from what we're trying to get, go back up here, we're trying to get is we want to have 3 H2s on the left, on our reactants side. So we're going to multiply the reaction C by 3, giving us 3 3/2 oxygen, right? So that'll cancel out there, and giving us 3 water molecules here. Down a little bit. So you can see on both sides we have 3/2 oxygen. Get rid of those. We have 3 water molecules. We can get rid of those. We have 2B, 3H2O, 3 H2s, B2H with our new enthalpy, and then our last reaction here, add the 4th one, multiplying that by 3. And so here we can cancel out our 3 H2Os on both sides there, giving us, this is just turning it into, changing the state of matter, so we can cancel out our liquid H2O, so it's in the gas phase. We can cancel those as well. So they all cancel, and so we get our reaction, add the enthalpies, and all happy.